All right, we're on to the next section, section 3.3, basic vector arithmetic. So let's go to the PowerPoint. And okay, it says both A equals B only if A equals B. And what that means is vector A equals vector B only if the magnitude of A equals the magnitude of B. Both point in the same direction along parallel lines. Now, the truth is that all of these, all the vectors that it shows you there on this XY coordinate graph, they're all the same vector. I mean, you can take a vector and move it wherever you want. There's nothing, this is a conceptual construct to help you visualize physics. These aren't physical quantities in and of themselves. So you can move those. You can move a vector wherever it is for your convenience to manipulate it and add it or subtract it, whatever you need to do. Vector addition. You'll see that there's a couple of methods. We're going to learn a few. Well, basically two methods. The graphical method, where you actually put pencil and paper and a protractor and a ruler and you draw these things out. And we're going to use components. That's not in this section, though. The component is the better way to do it. So if you add A plus B, you take vector A, and at the tip of vector A, you put the tail of B and draw it. Now, the resultant is from the tail of A to the tip of B. So R equals A plus B. Now, you can do this multiple times with multiple vectors. You hear on the right-hand side, we see R equals A plus B plus C. It's three vectors in a row, and it's all tail to tip method. There's the dogs barking. I told you that we'd be hearing them throughout. All right, now let's show that I'm sorry, A vector plus B vector equals B vector plus A vector. That is, there is a commutative law of addition. So it doesn't matter which order you add them in, you'll get the same resultant R. There's also an associative law of addition. A plus B plus C equals A plus B plus C. Verbally, I tried to group them. May not have come off, but you can see it certainly visually on the slide. Now let's show graphically that A plus B, which is the lower side of this image, is equal to B plus A. In one, you draw A and then you add B to it. In the other, you draw B and add A to it. And you'll see that you get the same resultant. B plus A equals A plus B. So there is a commutative property of vectors, vector addition. Okay, now vector subtraction and scalar multiplication. Now, the best way to subtract, or one way to think about vector subtraction, is if you take A plus B and you reverse the direction of B and add them, you essentially get A minus B. So you can see the dash line is where B would be drawn if you were adding it to A. But if you draw the reverse of it and add them, that's A plus a minus B. That's the same as A minus B. You get the result on the side there. Now, vector C is equal to A minus B. It's the vector we must add to obtain B, add to B to obtain A. And if you look, the A minus B on the A and on the left-hand image is the same as the C in the right-hand image. So that's how you subtract vectors. Of course, A plus minus A equals 0, and A plus B, or I'm sorry, A minus B equals A plus a minus B. Now, for as far as multiplication goes, the scalar multiplication, m times a, m times vector a, you will not change the angle of a. You may reverse its direction if n is a negative scalar, and you can, if it's, let's say m is 5, if you have 5a is 5 times as long as the original a, and let's say it's 1/3 a, it would be a would shrink down to 1/3 its size, and if it was minus 1/3, it would shrink down to 1/3 its size and reverse direction. So that's how you handle multiplication. Scalar can multiply a vector with no problem. We'll learn later on that there's two multiplication processes for vectors and vectors: the dot product and a cross product. A scalar product and a vector product are other names for it. So let's take a quick quiz. The magnitudes of two vectors A and B are A equals 12 units and B equals 8 units. Which pair of numbers represents the largest and smallest possible values for the magnitude of the resultant vector R equals A plus B? You have A, 14.4 units and 4 units, B, 12 units and 8 units, C, 20 units and 4 units, or D, none of the answers above. And I'll give you time to think about it. Okay, that's enough time. Now, let's say you have A equals 12 and B equals 8. If you were to put them one on top of the other in the same direction, what would your result be? 12 plus 8 is 20. So 20 is the maximum. Now, what if you were to reverse the B, which is 8 units, in the opposite direction of A? It would be 12 minus 8 is 4 units. So the correct answer is C, 20 units and 4 units. Now let's look at another quiz question. If vector B is added to vector A, which two of the following choices must be true for the resultant vector to be equal to 0? A and B are parallel and in the same direction. Let me just read the options and let you think about it. A and B are parallel and in opposite directions. A and B have the same magnitude, or A and B are perpendicular. So think about it a little bit. Now let's think about each of these answers. If A and B are parallel and in the same direction, then they would add. Now, if A and B are parallel in an opposite direction, well, that's an improvement, but it doesn't quite give the whole answer. So A and B have to be parallel and in opposite direction, but there's one more stipulation. They have to have the same magnitude. In order to cancel out, they must have the same magnitude. And if they are perpendicular, then that's not going to give a resultant. You're going to get a resultant that's basically, I would say, a hypotenuse, but it doesn't necessarily have to be a right angle. So the answer is there's two, B and C. They are parallel and in opposite directions, and they have to have the same magnitude. Okay, now let's look at an example problem. A car travels 20 kilometers due north and then 35 kilometers in a direction 60 degrees west of north as shown in the figure. Find the magnitude and direction of the car's resultant displacement. Well, first let's conceptualize the vectors A and B that appear in the figure help us conceptualize the problem. The resultant vector R has also been drawn. We expect its magnitude to be a few tens of kilometers. The angle beta that the resultant vector makes with the y-axis is expected to be less than 60 degrees. The angle that vector B makes with the y-axis. Okay, now let's categorize. We can categorize this example as a simple analysis problem in vector addition. The displacement R is the resultant when the two individual displacements A and B are added. We can further categorize it as a problem about the analysis of triangles. So we appeal to our expertise in geometry and trigonometry. Okay. So if we analyze this problem, in this example, we show two ways to analyze the problem of finding the resultant of two vectors. The first way is to solve the problem geometrically, using graph paper and a protractor to measure the magnitude of r in its direction. In fact, even when you know you are going to be carrying out a calculation, you should sketch the vectors to check their results, to make sure that it's reasonable. With an ordinary ruler and protractor, a large diagram typically giving answers to 2 digits, but not to 3-digit precision. So you can't, it gives you an approximation. The second way to solve the problem is to analyze it using algebra and trigonometry. The magnitude of r can be obtained from the law of cosines as applied to the triangle in the figure. So use r squared equals a squared plus r squared equals a squared plus b squared minus 2ab cosine theta for the law of cosines to find r. You substitute the numerical values, noting that theta equals 180 minus 60, which is 120 degrees. So that becomes this equation. And use the law of sines to find the direction of r, measured from the northerly direction. So sine beta over b equals sine theta over r. Sine beta equals b over r sine theta. And you end up with 35 kilometers divided by 48.2 kilometers times the sine of 120 equals 0.629. And so the beta, you take the arc sine of that, you get 38.9 degrees. So let's see if I think I have all the, okay. Now, does the angle beta that we calculated agree with an estimate made by looking at the figure, or with an actual angle measured from the diagram using the graphical method? You take a little protractor and check it out. Is it reasonable that the magnitude of r is larger than that of both A and B? Well, it's not quite a hypotenuse because it's not a 90-degree angle, but it should be longer than each of A and B. Are the units of r correct? And so those are things to consider as you solve this problem. Although the head-to-tail method of adding vectors works well, it suffers from two disadvantages. First, some people find using the laws of sines and cosines and sines to be awkward. Second, a triangle only results if you are adding two vectors. If you are adding 3 or more vectors, the resulting geometric shape is usually not a triangle. Later, we'll explore a new method of adding vectors that will address both of these disadvantages. And let me find my place. I think there it is. Okay. Suppose the trip were taken with two vectors in the reverse order, 35 kilometers at 60 degrees west of north first, and then 20 kilometers due north. How would the magnitude and the direction of the resultant vector change? Now think about it. What did we discuss earlier? We discussed the commutative law of vector addition, so they would not change. The commutative law for vector addition tells us that the order of vectors in an addition is irrelevant. Graphically, we see that the vectors added in the reverse order gives us the same resultant vector. So B plus A gives you the same R as we got earlier. Now, this ends our discussion of basic vector arithmetic. The next section, section 3.4, it'll be the last section of the chapter. It will cover components of a vector and unit vectors. And component of the vectors are the better way to do vector addition. And you'll be doing that on Monday with the vector table laboratory experiment. Okay, thank you. Stop share.